So good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So today is our week 11 session. So uh, let's have a brief overview of what are the things that are covered in the week 11 lectures. So it's sort of continuation from the week 10 topics of heat radiation. So in week 11, we discussed about the Kirchhoff's law, where the emissivity it is equal to the absorptivity of a body under defined conditions or assumptions. So that assumptions and conditions are clearly discussed in the lectures. So uh, s- then it is moved on to the view factor. How to find view factor, that is a part of radiation at a striking onto a surface. So the concept of view factors were discussed. Then radiation networks. So radiation networks were introduced. So we will discuss some of the questions based on these topics today. So let's get started with the first question. So the first question, we have a diffusely emitting surface is exposed to a radiant source, causing an irradiation on the surface too. So irradiation is given. The intensity of emission is also given, and the intensity for emission is so the intensity of emission of the surface is also given, and the reflectivity of the surface is also given. So we need to find out the radiosity and also the net heat flux from the body. So I have a surface here. So which is say at some temperature T. Okay. So some radiation is striking, which I am denoting it as G. And a part of this radiation will be reflected, that is G reflected. And because of this temperature of the body, some energy will be also emitted as emissive, will be emitted by the because of this temperature. That is, I'm considering it as E. So these are the energy interactions that are happening to a surface. So we are considering this is a diffuse surface. So the given conditions I am writing. So this is a diffuse surface. So the intensity of radiation is independent of the direction. So we can write emissivity E is equal to pi times I, that is intensity. That is what we can get from this question. And also the reflectivity rho of the surface is given, that is 0.8. And yeah, so we are assuming that there is no transmission or the as it is not mentioned clearly, we are assuming that uh, so we can assume that it is an opaque subject. It's not necessary anyway, but yeah, for solving this question, this assumption is not required. But so because of that, I'm not writing it. So the answer to the question means the what we need to find is the net heat flux and the radius. So what is meant by radiosity? Radiosity is the radiosity accounts for all the energy or the radiant energy that is emitted from the surface. All the radiant energy from the surface. I'm denoting it as okay. So G is the radiation. So these are the given surface. So what is the net heat flux? So we are asked to find out radiosity. So radiosity is, I'm denoting it as J, which is equal to G reflection plus E. right? So radiosity accounts for all the radiant energy that is emitted from the surface. So whatever say part of the incident radiation is emitted, that is G reflection, and also some amount of uh, energy is emitted by the body itself because of by virtue of its temperature. So, so G reference is equal to rho times G. That is reflectivity is given, that is zero point 0.8 times G, that is 1000. So that is 800 watts per meter square. Okay. Then E we have to find out. So it is given, the intensity is given, and also it is set as diffuse. So from that we can find out E is equal to, for a diffuse body, is equal to pi I, that is pi times, that is 143. So the answer will come out to be 449.02 watts per meter square. So this is the emission by the body. So the radiosity J is equal to G reflection plus E is equal to 800 plus 449.02 is 1249.02 watts per meter square. So this is the energy that is leaving the surface. So we are asked to find out the net heat flux from the surface. Net heat flux, that is energy, that is flux in, that is Q double dash in minus Q double dash out. What is the energy that is coming? That is, it is a irradiation. That is, it is given, that is 1000 watts per, minus what is the energy it is leaving the surface, that is 1249.02. So the net heat flux that is going out of the body, we can write it as 2 minus. Why this is minus? Because the body is losing heat. It's not gaining heat. The surface is losing heat. Okay. Answer is right. So there is some mistake in this in the option. So it should be 249. So the final answer is right. So the this is the heat flux that is emitting from the surface. So let's move on to the next question. So a horizontal semi-transparent plate is uniformly a similar kind of question only. Is uniformly radiated from and above the above and below. So a plate is there. So from above the surface, from above and below, it is irradiated, uniformly irradiated, while air is flowing over the top, both top and bottom surface. So I have a plate here. So air is flowing at both top and bottom surface. Okay. So providing a convection coefficient of 40 watts per meter square Kelvin, both. Okay. And the absorptivity of the plate to the irradiation is given as 0.4. That is absorptivity, that is alpha, is given as 0.4. And under steady state condition, the radiation detector above the surface indicates a radiosity of 500 watts per meter square. So I am denoting the radiosity as J. So from both top and bottom, we have a radiosity J of 5000 watts per meter square, which is detected by a device. So the surface temperature is given as 350 Kelvin. We are asked to find out the irradiation, that is G, that is coming to the surface from both top and bottom, and check whether the plate is a gray body. So first, under steady state, whatever E in, that is whatever energy it is coming, it should leave out, right? Then only steady state conditions will happen. So whatever that is energy that is coming, that is 2 times G, that is from both surfaces. And there is another loss also there, that is convection losses, because air is flowing. So normally heat will be transferred from by convection also. 2 times G should be equal to, so whatever energy uh, it is receiving, okay, it should emit. Then only the steady state conditions will occur. So 2 times Q convection plus 2 times J. So we can simplify as G is equal to Q convection plus J. So this is the irradiation. Okay. So Q convection, we know what is Q convection, that is H T S minus T infinity. H is given 40, Ts is 350, and air is at 300. So it is around 2000 watts per meter square is the Q convection. So the irradiation G is 2000 plus J already given 5000. It is 7000 watts per meter square is the energy that is coming to the plate. And under steady state condition we are talking about. And first, next we have to check whether the plate is gray or not. So for gray surfaces, we know for gray bodies, the absorptivity should be equal to emissivity. Right? So then we have to find out epsilon. We have to find out the emissivity epsilon. And if both absorptivity and emissivity are equal for this body, then the body is a gray body. So how to find out E? We know J is equal to E plus so whatever so at steady state conditions, Q net should be 0. That is, there should be no, means there is no net heat flux that the body should have. That is, Q net should be 0. So we are given with it is given semi-transparent body. Okay. So we are not considering about reflectivity here. Okay. So J is equal, so it is equal to, it should be 0. So J should be equal to E plus rho G plus, that is the energy that is reflected plus the energy that is absorbed. Okay. So sorry, it's a semi-transparent body, right? So reflected plus transmitted, that is what the radiosity, that is a part of energy will be reflected, that is incident energy, a part of it will be transmitted, it is and semi-transparent, so some part will be transmitted. So E plus G into rho plus tau. We know alpha plus rho plus tau should be equal to 1. So what? Rho plus reflectivity plus transmittivity should be equal to 1 minus alpha. That is E plus 1 minus alpha times G should be equal to J. So J is already given. So we can E is equal to epsilon sigma Ts raised to 4. So if we substitute all these values, we will get 5000. So what is the 5000 is equal to sigma Ts raised to 4 plus 1 minus alpha is also given, that is 0.4. G we already find out, that is 7000. So if we calculate this, okay, if we calculate this, you will get the answer as 0.94. So the emissivity of the body is 0.94 and absorptivity is 0.4. So both are not equal. So the body is not gray. I hope this was clear. So the first one was simple. That is, at steady state condition, there should need be means whatever energy that is coming should be leaving. Then only we can have the steady state condition. So whatever energy that is coming to the, that is as irradiation, it should be leave. It should leave the body. So the radiosity will be equal to the, this radiosity will be, what is the radiosity? That is the energy that is leaving, the radiant energy that should be specified, the radiant energy that is leaving the surface. So that radiosity will consist of the emissivity, means emissive power. That is the body, that is the energy that is emitted by the body because of this temperature, its temperature, plus a part of the reflected radiation, reflected irradiation, and also it is specified that the body is semi-transparent, so some part of the radiation will be transmitted. So all this will account for the radiosity, that is the total radiant energy that is uh, emitted by the surface. So this J is given. From that we find out the epsilon. So we find out that both epsilon and absorptive, that is emissivity and absorptivity is not same. So it is not a gray body. So let's move on to the next question. So I know it's also a similar kind of question. So an opaque gray surface at 27 degrees Celsius is exposed to irradiation of 1000 watts per meter square, and this much is reflected. An opaque is given that opaque. So if it is opaque, means there is no, that is tau is equal to 0. That is, there is no transmitted radiation. Then so an irradiation is coming of 1000 watts per meter square. Okay, and a part of this is reflected, that is G. This is G, that is irradiation. G reflected is given in the question, that is 8000 watts per meter square. So air is flowing. So some convection loss is also happening. That is, air is flowing at 27 degrees Celsius. So We convert to Kelvin, that is 290 Kelvin. And the heat transfer coefficient is also given, that is 15 watts per meter square Kelvin. We have to determine the net heat flux from the surface. That is, to find is Q net. So there will be some convection losses also coming. So first we will find out that it is Q convection is equal to H T S minus T infinity. That is H is given as 15 into 27 minus 17. 15 into 10, that is 150 watts per meter square is the convection losses. So here we are not only considering the top surface, because if it is not specified that the bottom surface is also participating in heat transfer. But if it is specified clearly in the question, we should also consider. So, so what is the energy that is coming in? That is Q in is the irradiation, that is 1000 watts per meter square. What is a Q out? That is G reflection plus Q convection plus the emission from the. So our task is to find out this E. For finding out E, we need to find out what the emissivity. Okay. So we know yeah. So our task is to find out this emissivity. So how to find out? So first we will find out the reflectivity. Rho is equal to GF divided by G. It is given 800 divided by 1000. This is 0.8. And also we know the absorptivity plus reflectivity plus transmittivity is equal to 1. And also it is an opaque body, so this transmittivity is 0. Okay. So alpha plus, that is absorptivity plus rho, is equal to 1. So absorptivity is equal to 1 minus rho, which is 1 minus 0.8, it is equal to 0.2. So it is specified in the question that this is the body is gray or the surface is gray. Surface is gray. So by Kirchhoff law, alpha is equal to eta. Okay, because it's a gray surface. So now our question is so that we got point, that is the emissivity also. So emissive power is equal to 0.2 into 5.67 into 10 raised to minus 8. That is surface is at 27 degrees Celsius. So we have 300 raised to 4. So E is equal to how much? So if you calculate, you will get 91.854 watts per meter square as the answer. That is the emissive power of the body. Okay. So what is Q net? Q in, that is given, that is G minus E plus, that is radius E plus, that is Q convection plus rho times G reflection. Okay. So if we calculate this, that is G is given, that is 1000 minus 91.854 plus 150 plus this G reflection is already given, that is 800. So if we calculate this, we will get as minus 41.854 parts per minute. So as it is, so the as the minus is given, it is because the body, the surface is losing heat. Okay, so process answer is option A. So the surface is losing heat. I hope this question was clear. So it was a similar kind of question we already did for question 1 and 2. So next we have the question number 4. A small solid metallic sphere as a opaque diffuse coating for which we have this variation of the absorptivity of the radiation of the body is given. The sphere, which is initially at a uniform temperature of 300 Kelvin, is inserted into a large furnace whose walls are at 1200 Kelvin. Determine the total hemispherical absorptivity and emissivity for the final steady state. So at final steady state means that initially there is a temperature difference, that is the pole is at 300 Kelvin and the walls is at wall is at 1200 Kelvin. So after steady state means after infinite time, may not be infinite time, but after some time at steady state conditions, both the temperatures should be of the body will be same. So like that, the temperature equilibrium will happen. So we have to find out the absorptivity and emissivity at that time. Okay. So we have the lambda here and we have the alpha. This is alpha 1 is equal to 0.8. This lambda is 5. And this alpha 2 is equal to 0.1. So it has a distribution, spectral distribution of absorptivity. So what is meant by, so the definition of absorptivity, it's already discussed in the lectures, that is alpha t is equal to integral 0 to infinity alpha lambda t e lambda t dt whole divided by eb lambda t. Okay, ebt, not lambda t, ebt. So this is our expression for absorptivity. So here in this question, T is equal to 1200 Kelvin. Okay. So we are, as it is divided into two, means we are splitting this, that is 0 to 5 alpha 1 lambda 1200 eb lambda 1200 dt divided by eb 1200 plus 5 to infinity alpha lambda 1200 eb lambda 1200 dt divided by, sorry, d lambda divided by eb 1200. So this alpha is equal to alpha 1. I am taking this as alpha 1 times, what is this, integral 0 to lambda 1 eb lambda t d lambda divided by ebt. So that is the black body radiation function, that is f 0 to lambda 1 plus lambda 2 times f in that region, that is lambda 2 to infinity. So this lambda 2 to infinity, because it's from lambda 2 to infinity, this function should be uh, uh, the summation of these functions of these all these functions in this for the range of lambda should be equal to 1. So f lambda 2 to alpha infinity should be equal to 1 minus this not lambda 2 lambda 1 f of 0 to lambda 1. Okay, so here lambda is equal to, here lambda is equal to 5. There is no lambda 1, it's lambda only. So here, so this alpha is distinguished between means this much one region, this much another region. So this lambda is given. Okay, so we can find out what is f 0 to lambda, where lambda is equal to 5 micrometer. So for that we need to find out lambda t, that is 5 into t is 1200, that is 6000 micrometer Kelvin. So this I have taken from the Incoopera book. Okay, so this black body radiation functions is given. So lambda t 6000 we have to search. Okay, so 6000 is here. So this is the lambda t 6000. Okay, so the black body distribution function, that is f 0 to lambda, for that is given as 0.737819. So we can substitute this in this equation, that is lambda 1, it is given as 0.8, 0.8 into 0.737819 plus the next one is 0.1, 0.1 times 1 minus 0.737819. If you substitute this, you will get the answer as 0.6164. Okay, which we can approach at 0.62. So as it is a steady state, means as both the ball, so as it is at means as both the ball and the surface from which the ball is getting radiation is at same temperature. So we can apply Kirchhoff rule, that is alpha is equal to emissivity, which is equal to 0.26. So from that, only when, so that is one condition for this using the Kirchhoff law. So when both the uh, radiating surface and the surface which is getting radiation both are at same temperature, we can use the Kirchhoff law, that is alpha is equal to mc, that is absorptivity is equal to emissivity. So for example, if it was not, means we are asked to find out the initial case, for the initial case, then the alpha will not be equal to epsilon, because the alpha will be the procedure for finding out alpha will be same, epsilon will be also same, because alpha 1 is equal to means alpha lambda is equal to epsilon lambda. This is true for any case. So this will be equal to epsilon, that is alpha for 0 to lambda, alpha 1, alpha and epsilon will be same, and from lambda from 0 to 5, alpha and epsilon will be same, and from 0 5 to infinity also alpha and epsilon will be same. So but the total will not be same. I hope you understand. This is because of the spectral distribution. So when we calculate the emissivity, that is emissivity of the ball is at which one? Initially the ball is at 300 Kelvin. So when we use the black body radiation function, we should consider the lambda T, that is lambda as 5 into the temperature as 300. So we should consider the black body radiation function corresponding to lambda T is equal to 5 into 300, that is 1500. Okay, the rest of this are same. So the calculations are same. So as it is at fine steady state condition, that is both the body and the wall are at same temperature, we can use the Kirchhoff law and say that alpha is equal to mc. Okay, I hope this was clear. So let's move on to the next question. That is, this is a question from the view factor. So we have a solid cylinder is located at the center of a hollow sphere. So we have a hollow sphere and we have a solid cylinder that is located at the center. So this surface is given to, okay, the diameter of the sphere is given as A1 is given as 1 meter, and the cylinder diameter is given as 0.5, and also the length or height is also given as 0.5. We are asked to find out what is the view factor F22. Okay, that is from the cylinder F has to find out F22. Not F22, it's F11. Sorry. We are asked to find out what is F11. That is from this surface to this surface itself, because it's a curved surface, right? So some part of the radiation that is emitting from this surface can fall on the same surface itself. That is F11. So from reciprocity theorem, we know A1 F12 should be equal to A2 F21, right? F1 to 2 also we know F11 plus F12 should be equal to 1, because whatever radiation that is emitted from this sphere, it should, a part of it will be falling on to the cylinder and part of it will be falling on itself. So so the sum should be equal to 1, right? So we are asked to find out F11. So F12 we have to find out. So F21 will be equal to F21 will be equal to 1, because whatever the emission that is the cylinder is emitting, it will not fall on the cylinder at all, because if you can you can imagine from the geometry itself, so it will not fall onto the cylinder. So whatever the radiation that is emitted from the cylinder, it will fall on the sphere. That is F21. That is from 2 to 1, it will be 1. What complete radiation it will fall. Okay. So we can find out F12 from A1 by A2. Sorry, A2 by A1 into 1. So A2 is pi d square, is two surfaces, 2 pi d square. Sorry, 2 times pi by 4 d square, these two surfaces, and the curved surface, that is plus pi d L divided by what is inner surface area, that is 4 pi r square or r1 square we can write, or what to say, pi d square. Okay. So if we substitute these values, we can get 2 into pi by 4 into That is d2 square, 0.5 square plus 5 into 0.5 into zero point 0.5, the whole divided by 4 pi into zero point 0.5 the whole square. Okay, so the answer will come out to be around 0.375. So we find out F12. From this equation, we know F11 plus F12 should be equal to 1. So F12 should be equal, sorry, F11 should be equal to 1 minus F12, which is 1 minus 0.375, which is equal to 0.625. Okay, the answer is B. So we'll move on to the next question. It's also a similar kind of question. Yeah, here the question. Here we have to find out the F22. Okay, so that is this question for change. Okay. So in this is a circular tube of equal length and diameter. That is D is equal to H. Okay. So the view factor of F1 to 3, it is given as 0.17, and we have to find out F22. How? So we can divide this into three surfaces as I said, from top, bottom, and side. So I have given name also as 1, 3, 2. So whatever the emission that is emitted from the one will fall on 2, a part of will fall on 3. Like the same case, whatever emission, but it will not fall on to itself. That is F11 will not occur because it is flat. So it's the same case from 3, some part will fall on 1 and some part will fall on 2. For 2, but as it is curved, some part will fall on 1, some part will fall on 3, and some part will fall on itself. That is, if I write the this uh, view factor of 2, I can write F2 to 1 plus F2 to 2 plus F2 to 3 should be equal to 1. Okay. But if you see, because of symmetry, F21 will be equal to F23. Both will be same. Because it's like both have, it's like in the mid, because you see whatever emission that this surface will give to this side, the same will emit to this side also. Okay, so that's why we are using the symmetry, that is F21 will be equal to F23. So if we find F22 will be equal to 1 minus 2 times F23, or 1 minus 2 times F21, both are same. So our task is to either find out 21 or 223 to get F2. So A1 F13 will be equal to A3 F A3 A3 F31, right? So if I am taking the case of A13, that is case 1, 1 3 plus 1 1 2 should be equal to 1, right? It's already given because whatever energy that is falling is emitting from the 1, it should fall on 3 some part and the rest will fall on 2. That is F13 plus F12 should be equal to 1. So F12 will be equal to 1 minus F12. F12 will be equal to 1 minus F13. that is 1 minus 0.17, that is equal to 0.83. Okay. And also, so we now A1 F12 will be equal to A2 F21. So what we need to find out is AF21, because to find out this F22 from this relation, A1 by A2 divided by F12, A1 is equal to pi by 4d square, A2 is equal to pi dh into 0.83. Pi cancel, d by 4h into 0.83, both are same. So you will get as 0.205. Now substitute this into this equation, that is F22 is equal to 1 minus 2 times 0.2075. So the final answer will come out to be 0.585. I hope this was clear. So you need to just visualize how the radiation will go when we solve this radiative factor equation. So let's move on to the next question. So a cryogenic fluid is flowing through a 20 mm diameter tube, the outer surface of which is diffuse and gray with an emissivity of 0.02 and temperature is given. The tube is concentric with a large tube of 50 mm diameter. The inner surface of which is diffuse and gray with an emissivity of 0.05 and temperature also given. And the space between them is evacuated, because to restrict the other two modes of heat transfer, that is conduction. There won't be much conduction, mainly convection. If a thin walled radiation shield that is diffuse and gray with an emissivity of 0.02 on both sides inserted midway between the inner and outer surfaces, calculate the change in heat transfer per unit length of the inner tube. So we can, so the question is, we have a tube through which the liquid cryogenic fluid is flowing, and over to which we have another tube. The space between them is evacuated, so which means only radiation is happening. So that is case one. In case two, we have another concentric tube, which is we called as radiation shield. So if we place this radiation shield, what will be the change in heat transfer, right? Change in heat transfer or heat gain. So first we will consider the case one. We have a small tube and a big tube. Okay. So the outer surface is, I'm taking as 1 and this as 2. So if I am writing the drawing the radiation network, is heat will be lost from the 1 because that is at a low temperature. So EB1, that is the emissivity, that is epsilon 1 divided by epsilon 1 A1. Then we have the view factor resistance A1 F1 to 2. Then we have EB2, that is 1 minus epsilon 2 divided by epsilon 2 A2. This is the, so the next heat transfer Q will be EB1 minus EB2 divided by 1 minus epsilon 1 by epsilon 1 A1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by epsilon 2 A2. So we can find out each. EB1 is equal to sigma T1 raised to 4, which is 5.67 into 10 raised to minus 8 into 77 raised to 4. EB2 is equal to sigma T2 raised to 4, that is 5.67 into 10 raised to minus 8 into 300 raised to 4. And also we have A1. We are asked to find out, so the surface area is pi dl. So, but we are asked to find out per unit length. So this is pi d1. This pi times d1 is given as 20 mm. A2 is pi d2. that is given as 50 mm. So if you substitute all these values and also F12, that is this our inner tube can whatever radiation it is emitting or it is receiving, so it is emitting. It will not. It will entirely go to the outer of the tube. None of the part will come to the to one itself. So F12 will be equal to 1. So if I substitute these values and also epsilon 1 is given 0.02 and epsilon 2 is also given 0.05. So if you substitute these values into this expression, you will get the final answer as Q net as minus 0.5 watts per meter. So this will be the heat loss without radiation speed. So we have the next case, case 2. We have the smaller 2, we have the bigger 2. So this is the radiation shield in between, that is saying that it has put in the midway between the two. Okay. So if it is in the midway, diameter 1 is equal to this is 1 and this is 2 and this I am taking it as 3. D1 is equal to how much? It is 0.02. D3 is equal to 0.05. If it is midway, then D2 should be equal to 0.035 or we can say 35 mm. If I write the radiation network, EB1, 1 minus epsilon 1 minus epsilon 1 A1, we have the view factor A1 F13, 1 minus, and also it is active on both the sides, that is both the surface of the radiation shield is gray and diffuse. So you should consider the both surfaces. Epsilon 3 divided by epsilon 3 A3. This is EB3. Again 1 minus epsilon 3 the epsilon 3 A3. 1 by A3 F3 to 2 EB2. 1 minus epsilon 2 and epsilon 2 A2. So this we already calculated. This also we already calculated. So F13 is also same. That is F13 is also 1 and also like that F32 is also 1 because whatever it's because of this phase, whatever energy that is emitted by that group will be falling on to the this side. Okay. That is view factor. So the Q net will be EB1 minus EB2 divided by 1 minus epsilon 1 epsilon 1 A1 plus 1 by A1 F13 plus is 2 times 1 minus epsilon 3 divided by epsilon 3 A3 plus 1 by A3 F32 plus 1 minus epsilon 2 divided by epsilon 2 A2. Okay. This I already calculated, this already calculated, this already calculated, this already calculated. The only thing is to calculate this one. So it's also simple. A3 is equal to pi D3, which is pi times 0.035. And epsilon 3 is also given how much of the radiation shield, that is 0.02. So if you substitute these values into the expression, you will get the Q net case 2. This is case 1 as minus 0.25168 watts per meter. The question is the percentage change in heat loss, percentage change in heat gain, which is equal to Q net 2 minus Q net 1 divided by Q net 1, which I am writing it as, I'm taking the absolute values 2.1 divided by 0.501. Even if you put the negative, so that sign symbol, you will get the percentage in negative. So it is minus, plus, minus. Both are anyway negative. So the answer will be 49%. I'm taking the absolute value. So there will be a 49% reduction in the heat gain that you should consider. So there will be 49% reduction in the heat gain by the cryogenic fluid. It's a reduction. So the radiation shields are commonly used to reduce the radiation heat transfer. So that we'll discuss more clearly in the next lectures. Like Sir will be discussing about radiation shield in the coming in the vector topic. So we'll get more clarity when if you watch that. Okay. So here comes to the end of our session, and thanks for listening. And have a nice week ahead. See you next Monday, 6 to 7. Thank you. Thank you.